this is the experiment I've already conducted before uh, in a normal generator winding. We move the magnet. We move the magnet. So like let me so this is the highest volt. Let me bring it. Okay, it here. So this dot will be here. Okay, so in a normal conventional generator, we uh, we move the magnet. We move the magnet. We don't move the coil. So we only move the magnet. So that's why the braking effect, the Lenz effect is active in a normal conventional generator because we move the magnet. We move the magnet. So now you can see uh, this coil. This is a I think from a clever coil. So it has a plenty tons. It has a large number of tons here. So let me do the connection. Okay. So you can see I already connect the output terminal of the coil to the meter, to the multimeter. So let me make sure it is intact. Okay. So this is the magnet I have here now. This is the magnet I have here now. So when I bring this magnet close to this coil there will be an induced loss, induced magnetism. So you will see this metal will lead. So you can see the magnet is permanent. There is no any induced power here because the magnets have to be moving, either oscillating. So there has to be a movement so that the flux will be circulate or cutting. So now let's see. So I generate 4 volts, 5 volts, I generate 8 volts, 7 volts, 8 volts. So you can see. So if I place it here, I will be generating, but it will be minimal. Okay, let me put it on this body of the coil without touching the iron. There is a induced voltage. There is induced voltage, but minimal. So which means if you are rotating the magnet on around this coil, the voltage induced would be minimal. You can see 3 volts, and it has a less drag because the iron is not facing toward the coil. So yeah, I just rubbing the magnet on the body of the coil. Though there is a iron is attached because the magnet is strong. So you can see there is a display of voltage. Okay, now let me shift the magnet on the body, on the back of the coil, because you can see it has some distance, but than here the magnet is so close to the coil, but here it has some distance. So let's know if it will be an induced voltage. So you can see the induced voltage is somehow minimal because of the distance between the magnet and the coil. You can see. So there is no induced voltage, but when I press it here, same thing. Until I leave it here, then the induced voltage will be normal on the body. Okay. So now There is another thing I want to experiment. Now, I will put this magnet on the back of this coil. You can see I put this magnet on the back of this coil now. So now let me, this is a flat iron, I can easily bend it. This is a flat iron, laminated iron. So now let me know if it can generate some amount of voltage. Okay, I can, let me slow tape it so that people will not think it is because it has a surface contact. That's why it is generating. Let me use tape. Okay, let me cover the iron so it is not a direct contact. So I know that it is a induce. So but the voltage is minimal, the induced voltage is minimal. Okay, now let me use a about 3 mm thickness of iron. So let me, you can see I generated about 4 volts, 4 volts. So 4 volts, which means that if I could press this magnet on the back of this coil, once I do that, the whole of this iron will be permanent magnet, because iron is a good conductor of magnetism. So you can see the whole body of this iron is magnet. So now when I put iron here, it's like it already showed it. So immediately I put this iron out, it's like a magnetism, the flux is cut. So there will be induced voltage in this coil. You can see. So and from what I experiment with this such design is that even though when you shorten the coil, when you load the generator, it won't have a direct break, because only the iron is moving toward this coil. It is not magnet. It's not permanent magnet or electromagnet. So only this iron is moving here. You're just cutting the flaws, and there will be a induced voltage. But if you are using magnets to be rolling over the coil, once you load the output of this coil, or once you short circuit it, it will be breaking the magnet by opposing the motion. So even though, let me connect this LED bulb. Let me connect this LED bulb. Let me connect this LED bulb. You can see there is a display of current here. There is a display of induced power. Okay, so now let me also do it this way. Let me know if there will be an induce. There is also induce. There is also induce. So there is also induced power. And this bulb, there is also induced power. in this bulb. So which means even though use the magnet when we use the magnet, there will be the induction, yeah, the power, the flaws will be much, because you can see when I use magnet, I generated over 8 volts, 8 point something volts. But when I place iron, I generate about half of the power. But even though if we generated the half of the power, it is in a good shape, because when we load the coil, we won't have a direct uh, break in the loto, in the magnet that is moving. You can see we generate 8 volts. So, but let me press it and check the voltage we generated when we use iron. Okay, it's like we generated half of the voltage, half of the voltage when we use magnet. So it depends on the speed, uh, and the cutting of the flaws. So, but from what I understand about this experiment and this design is that it won't have a direct break in the motion. Assuming you are using motor to position it this way and rotating it, when you shorten this coil and when you load it, it won't have the effect in the moving of the armature or motor. It won't have any break. But if you're using a magnet, once you load this coil, due to the opposite pole, it will try to reduce the speed or shorten the speed of this the speed, or oppose the speed, which means that it will try to stop the speed. So, and the return of it, the motor will be consuming more current when you load it or when you shorten the coil. So this is exactly, if I can get this coil up to 4 or 5, I will try the experiment. Experiment. Maybe since the coil has a small gauge of wire, small conductor size, I will make it in parallel so that it will have more, it will power some meaningful load output. It has a huge amount of tons, but I think the size of the conductor is also small. So if I can get it something about 4 or 6, then I can combine it to give meaningful current output. So, but the demonstration is that, because the main important thing is that not about the voltage, the output from the coil, but when you put load, you're gonna find that the speed of the motor, the driver will decrease, and when the speed decreases, the current consumption will increase, and is what we're trying to avoid. So how we can avoid this by doing something like this, so that the magnet will be moving. The magnet will be at the back of the coil, held by the iron. Then we'll just be cutting the flaws, cutting the flaws, cutting the flaws. So I hope any of you can try the experiment out. I hope any of you can try it out. Let's see the out the results. Thank you.